We'll see the problems on motors. A 240 volt shunt motor takes a current of 80 amps. If the field winding resistance is 120 ohm and armature resistance is 0.4 ohm, determine the current in the armature, the back EMF. The circuit is as shown below. We need to find out the current in the armature, that is IA we need to find out, and back EMF EB we need to find out. First of all, you should know one of the things we need to find out. The diagram is as shown like this. So it has been given the armature resistance 0.4 ohm and the field circuit resistance 120 ohm is given, and the voltage, the terminal voltage 240 volt, it has been given. It has given 240 volt this shunt motor takes current of 80 amps. So takes in the sense is always a line current, takes current of 80 amps. So armature is taking current from line 80 amps. The field winding resistance and armature winding resistance has been given, and we need to find out the armature current. So how we can proceed? We know that IL is equal to IA plus IF. So this IL is equal to this IA plus IF. So in the previous also we have seen that IL is equal to IA plus IF for a motor. So for that reason we need to find out IA and IF. How to find out IF? IF is equal to V by RF, that is V divided by RF. So what is voltage V? 240. RF field circuit resistance, shunt field resistance has been given as 120 ohms. So from this we can find out 2 amps. Once you find out IF is equal to 2 amps, we know that IL is equal to 80 amps is given line current. We can find out IA is equal to 78 amps. Then you can substitute back in EB, that is required back EMF V minus IRE. Here you have to substitute IA, the value of IA. So that is 240 minus 78 into 0.4. 0.4 armature resistance given. You will end up with 208.8 volts. Second problem. A series motor having a series field resistance of 0.25 ohm and armature resistance 0.15 ohm is connected to 220 volt supply. So that is, once again, there is V. By reading this problem only you have to find out what all things have been given. And a particular load runs at 20 revolution per second when drawing 20 amps from the supply. Calculate the EMF generated at this load. So at this load we need to calculate. Determine also the speed of the motor when the load is changed such that the current increases to 25 amps. From 20 amps to 25 amps current has been increased. Assume flux increases by 25%. So that you have to see. So it is drawing 20 amps. Fine. Armature current has been given straight away. So it drawing a current of 20 amps here. It is drawing 20 amps from the supply. So once again, a series field, only one current present, or that is IF, IA and IL are same. So we have E, generated EMF, or EB, the back EMF. Sorry, is the back EMF. Back EMF is equal to V minus IA into RA plus RF. 220 volt is been given, 220 volt. IA, only one current, 20 amps initially. This is the load, initial load. RA plus RF value have been given. We'll end up with 12 volts. When the current is increased to 25 amps, it has been given that when the load is changed such that current increases to 25 amps. What is generated EMF? E2. We need to find out. Generated EMF E is equal to, when current is changed to 25 amps. This will not change. This is also not changing. So only this is changing. So we can find out E2 as 210 volts. 210 volts. We have got formula E1 by E2 is equal to phi1 by phi2 into N1 by N2. So what is N1 and N2? These are the speeds. These are the speeds. So when E1 is there, that is 212, and is taking 20 amps current, flux is phi1 and speed is 20. When phi2 is there, that is it is given that flux is increased by 25%. Flux is increased by 25%. How we can substitute phi1 as I1 here? Phi1 as I, because in series motor flux is directly proportional to current. Since in series motor flux is directly proportional to current, so I can substitute here phi1 as phi1 and this you can see here as 20. Yeah, see here you can see here 20, phi1 as 20. And what is phi2? 1.25 times phi1. It has increased by 25%. And n2 as it is. So n2, what is the speed? n2. So n2 that we need to find out. Everything has been given. So once again, n1 speed is 20 rpm, revolution per second, rps, sorry, 20 rps has been given. Phi1, you can replace phi1 as phi1 is 1.5 phi1. Either you can give the value for phi1 or remain as it is. Anyway, phi1 will get cancels. So 1.25 phi1. So phi2 is equal to 1.25 of phi1. So if we replace like this, you will get n2 as 15.85 revolution per second or 950.9 revolution per minute. So in this problem, so flux is directly proportional to current. Either you can take phi1 as 25 and phi2 as 1.25 into 25, or you can remain phi1 as it is and 1.25 phi1, because phi1 and phi1 will cancel each other. In series motor, flux is directly proportional to current. That you have to remember. We can replace phi1 by Ia and this phi2 by 1.25 times Ia. That's all, one and the same. Problem number 3. A 350 volt shunt motor runs at its normal speed of 12 revolution per second when the armature current is 90 amps. So first it is normal speed 12 revolution per second RPS at armature current 90 amps. It is straight away is given armature current as 90 amps. The resistance of the armature is 0.3 ohms. RA is also given. Find the speed when the current is 45 amps and resistance of 0.4 is connected in series with the armature. The shunt field remains constant. Second, find the speed when the current is 45 amps and the shunt field is reduced to 75% of its normal value by increasing the resistance of the field. So there is some things we need to think about it. Okay, we'll go step by step. Find the speed when the current is 45 amps and the resistance of 0.4 is connected in series with the armature. So initially it is running very normally, so without having extra resistance in connected with the armature. So when it is running normally, what is E1 or EG or sorry EB? So back EMF or E1. So V minus IRE 350 it has been given. Armature current IA is given. Armature resistance is given. So 323 volts it is having back EMF when it is running normally. Now when the current is 45 amps, what is now E2? When you are calculating for E2, so current is changed, also a resistance is inserted in series with the armature. So 0.3 plus 0.4 you have to calculate. So from this you can calculate E2 as 318.5 volts. So what to find out the speed now? For this condition we need to find out the speed. So we calculated E1, we calculated E2. Now we need to calculate speed at this condition. At this E2 we need to find out, N2 we need to find out. How we can do it now? Shunt field remains constant. So that means say there is no variation in flux, because the fluxes are produced because of field windings. Fluxes are produced because of field winding. So shunt field remains constant, in a sense flux remains constant. When the flux remains constant, with this condition, E1 is equal to phi1 N1 by phi2 N2. So E1 is given, E2 is given, phi1 is constant. It will not change both the cases. That will cancel each other. 12, and this is initial speed 12 revolution per second, and N2 we need to find out. From this we will get N2 as 11.83 revolution per second. Coming back to the second case now. Now find the speed when the current is 45 amps. So now is 45 amps. Now E2 is 45 amps. Once again you have to compare with the E1. Now E2 is changed, now 45 amps. And the shunt field is reduced to 75% of its normal value. So 0.7551. You have to use the same formula, but here is given that shunt field is reduced to 0.7551. For this condition we need to find out E2. What is E2? Formula for E2, V minus IA RA. So V 350 minus IA is now 45 amps, RA is 0.3 amps. So in this condition it is not told to add extra resistance 0.4 ohm. So it has been told only there is a change in armature current. So you have to find out E2 such that 350 minus 45 into 0.3 you will get 336.5 volts. So once again you have to apply the formula 323 divided by 336.5, that is equal to phi1 N1 12 revolution per second divided by phi2. Phi2 is reduced to 75% of its normal value. The flux is reduced. Shunt field is reduced means flux is reduced. 0.75 phi1 N2. From this we can find out N2 as 16.67 revolution per second. Problem number 4. A series motor runs, we have to understand this is a series motor, runs at 900 revolution per minute RPM when the voltage is 420 volts. Current is 40 amps. Only one current here, IL, ISC, IA. Voltage has been given 420 volts. The armature resistance has been given as 0.3 ohms and series field resistance 0.2 ohms. Calculate the resistance to be connected in series to reduce the speed to 720 revolution per minute with the same current. So initially the speed is 900 revolution per minute. Next the speed is reduced to 720 revolution per minute. To reduce the revolution to 720 revolution per minute, what is the extra resistance that we need to connect in series with the armature? That is the question. Okay, fine. Now when it is running normally without connecting any external resistance, formula for a series motor, E1 is equal to V minus I into RA plus RSC. So series field, everything data has been given, armature resistance, series field resistance, armature current, everything has been given. We can find out 400 volts. Now initially it is running at 900 revolution per minute. Once again we have got formula E1 by E2 is equal to N1 by N2. It is they have not mentioned about the flux, so flux remains constant. If they have not mentioned about flux, so fluxes we can take it as a constant. The flux phi1 and phi2 are cancel each other. E1 by E2 is equal to N1 by N2. Flux is unchanged. So phi1 and phi2 get cancel each other. E1 by E2 is equal to N1 by N2. 400 by E2, we don't know E2. Speed they have mentioned like this. Second speed is 720, initial speed is 900. We can calculate E2. Once you calculate E2 as 320 volts, we have got formula here. E2 is equal to, in the second case, we need to add one extra resistance in series with the armature or in series with the series field resistance to reduce the speed to 720 RPM. So 320, the second voltage what you are getting, this is the, it will not change, 420, this is the terminal voltage minus 40, once again 40 amps the same current, as mentioned, the same current is also changing. 0.3 plus 0.2 plus R extra resistance to be connected in series. That means say extra R we need to calculate. This R you have to calculate. How to find out this R? So once again, by solving this equation we will get 2.5. So this R is equal to 2.5. So the extra resistance it has to be connected is 2.5 minus 0.5, that is 2 ohms. So extra resistance it has to be connected is this total, what you're getting is R, what you're getting is total is R. So this R is equal to 2.5 ohms. And this 0.5 it has to be reduced, so we'll get 2 ohm. Next, problem number 5. A series wound motor is connected to DC supply and develops a full load torque when the current is 30 amps and speed is 1000 revolution per minute. Series motor once again develops a full load torque when the current is 30 amps, IA, IL, ISC 30 amps. Speed is given N1, 1000 revolution per minute, RPM. Now, if the flux per pole is proportional to the current flowing, so flux per pole is, in a series motor, flux is directly proportional to the current. Anyway, we know that series motor, it has mentioned about this. And find the current and speed at half load torque when connected to the same supply. So torque is reduced by half. Torque is reduced by half. Now we have got general formula. Torque is directly proportional to phi into Ia. Okay, and if you consider two torques here, because the flux per pole is proportional to current, find the current and speed at half full load torque. So two cases we need to find it. One is normal torque, second is half full load torque. Fine. So we know that in series motor flux is directly proportional to current. So here, so T1 that is equal to, here T2 is half torque. T1 by 0.5 T1, that is equal to I1 square, because phi 1 directly proportional to I1, phi 2 directly proportional to I2. So 30 square divided by I2 square. From this we can calculate I2 as 21.2 amps. Now speed is directly proportional to 1 by I. Speed is directly proportional to 1 by I. We will get speed is directly proportional to 1 by I. N1 by N2. N1 by N2 or EB by phi. So already told N is directly proportional to EB by phi. In series motors, speed is directly inversely proportional to current. We know that N is inversely proportional to armature current in a series motor. While studying the characteristic of speed current characteristics, we have seen that speed is inversely proportional to armature current, so never start series motor without any load. So from this we got N is inversely proportional to current. We get N1 1 by I1, N2 1 by I2. So we will get I2 by I1, that is N1 by N2 is equal to N1 speed 1000 RPM, N2 find out the current and speed. So current we already found out, we have to find out this speed now. So substitute for I1 and I2, or I2 and I1. We will get N2 as 1415 revolution per minute. We will see problem number 6. Determine the developed torque and shaft torque of a 220 volt 4 pole DC motor with 800 conductors, wave connected, supplying a load of 8.2 kilowatt by taking 45 amps from the mains. The flux per pole is 25 millibare and its armature resistance is 0.6 ohms. In this gross torque, armature torque, developed torque all are same. We have got a formula for armature torque is 0.1595 ZP Ia by A. where A is equal to number of parallel path, we know that wave connected A is equal to 2, armature current is given 4 amps, P number of poles, 4 pole 45 amps, it is given armature current is 45 amps, 4 pole machine, 800 it is given as conductors, Z flux 25 milliweb. So everything has been given. You can find out the torque as a 286.2 Newton meter. Find out the torque. So next we need to find out the shaft torque. So what is shaft torque? Actually the shaft torque is 9.55 into output by N. What is output? Output, so two ways we can find out output. One is it is given 8.2 kilowatt, actually 8.2, it has to be 8.2 10 raised to 3. So 8.2 10 raised to 3, 8 kilowatt actually. So it has to be 10 raised to 3, 9.55, 8.2 10 raised to 3 divided by 289.5, we will get 270.5 Newton meter. So from this we can find out the shaft torque. So output is given 8.2 kilowatt, 9.55 divided by N, speed 289.5. So how to get the speed as 289.5 rpm? So from this we need to use this equation, EB is equal to 5ZNP by 68. To use this equation, EB is equal to 5ZNP by 68. So speed is unknown, EB is unknown. To find out EB, we are using VB is equal to V minus IARA. So V 220 volt given, armature current 45 amps, RA is given. We can find out EB. Once you find out EB, so we can directly substitute this. EB 193 is equal to 25 milli into N 800 rpm, 4 pole, speed as it is, and 60 into A. So from this we can get N as 289.5 rpm. Once you get N as 289.5 rpm, so then you can substitute here. Shaft torque is given by 9.55 output by N, 9.55 into 8.2 10 raised to 3 divided by 289, we will get otherwise we will get 270.5 Newton meter. So yes, problem number 7. A 250 volt DC shunt motor on no load runs at 1000 rpm and takes 5 amps. The total armature and shunt field resistance are respectively 0.2 and 250 ohm respectively. Calculate the speed when loaded and taking a current of 50 amps if the armature reaction weakens the field by 3%. Weakens the field by 3%. There's the meaning is the armature reaction weakens the field by 3%. So what is it? A 250 volt shunt motor on no load runs at 1000 rpm and takes 5 amps. Calculate the speed when loaded and taking current of 50 amps if the armature reaction weakens the field by 3%. So it has to be weakens the field. The weakens has been missed here. Weakens the field by 3%. Fine. Here we need to find out E1 in normal condition. So E1 is equal to V minus IA1 RA. So what is V 250? What is IA? The armature current is given by IL minus I shunt. For a shunt motor, armature current is equal to IL minus I shunt. Load current 5 amps. It takes 5 amps load current minus shunt field current. Shunt field current is given by V by RSH. 250 by shunt field resistance has been given 250. So 1 amps. So 5 minus 1, 4 amps. Once you are able to find out IA1, we can find out E1 as 249.2 volts. So this much you have to do. So next, now armature current when loaded. So that is I is equal to IA2. Now second current. So that we need to find out. It has been given as calculate the speed when loaded and taking a current of 50 amps. So that means say now load current is has been changed as 50 amps. Shunt field current will not change because they are not mentioned about shunt field. Only load current has been mentioned. So 50 minus 1, 49 amps. IA2, the new armature current is 49 amps. When IA2 is changing, definitely IA2 is related with E2. The back EMF, it will also change as 240.2 volts, because V is constant, IA2 will change, RA is not changing, but the total value E2 will change to 40.2 volts. Given once again, the armature reactions weakens the field by 3%. So that means say the new value of flux, when you have to calculate the speed taking a current of 50 amps, the new value of flux is 0.9751. 0.9751. So we have got formula, N is directly proportional to EB by 5. So if we substitute N1 and N2, N1 is directly proportional to EB1 by 5.1, N2 is directly proportional to EB2 by 5.2. If we do N1 by N2 or N2 by N1, we will get this formula, E2 5.1 divided by E1 5.2. So E2 240.2 into 5.1 divided by E1 249.2 into, what is 5.2 now? 3% has been reduced, so 0.9751. So from this we can calculate N2 as 993.69 RPM.